Happy Halloween, everyone, and welcome to today's webinar in the CERDUP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosynta Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDUP and ESTCP. The webinar will consist of a brief overview of both programs, followed by the technical portion, which features research on developing and demonstrating non-toxic and sustainable coating systems for military platforms. We'll start off with Ms. Elizabeth Hasselbeck from the Naval Surface Warfare Center, Carderock Division. And Liz will discuss the impact of cleaning tools on the wear of biofouling control coating systems and copper and zinc release. Her presentation will be followed by a brief Q&A session. Our second speaker will be Mr. John Escarsega from the U.S. Army Research Laboratory. And John will discuss advancing coating systems for Army tactical assets, including work completed, the product's transition to the field, and the vision of future coating systems for Army use. John's presentation will also be followed by a Q&A session, and we will conclude the webinar with a longer Q&A involving both of today's speakers. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use with Zoom. If you lose the content on your screen or if your screen freezes, try keying in Control and F5 to do a hard refresh of your browser. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience technical difficulties, we encourage you to use the call-in number provided here and make sure to enter the required ID number. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. Please reserve the chat box only for comments related to technical difficulties. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit your questions well in advance of the Q&A sessions. And when you do submit your question, please add your organization number, a name at the end of your question so that we can identify you during the Q&A period. With that, I would like to introduce Dr. Robin Eaton, who is the CERDUP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining CERDUP and ESTCP, Robin worked at Navarre's Weapons Division, China Lake in California. Robin?
Thank you, Rula. And first of all, since you started with Happy Halloween, I'll start with congratulations to the Nats and all of their fans who were up way too late last night. Okay, so CERDUP is the Strategic Environmental Research and Development Program, and it was established in 1991 by Congress as a partnership between the DoD, Department of Energy, and the EPA. CERDUP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDUP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. In this program, we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments performed under CERDUP or other research programs and are designed to transition technologies out of the laboratory and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDUP and ESTCP are complementary programs with much of CERDUP's R&D occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting laboratory efforts are conducted. there are 4 program areas in CERDIP and 5 in ESTCP. Installation Energy and Water program is ESTCP only, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms, are both CERDIP and ESTC programs managed jointly by a designated program manager. Now, today's webinar presents research and demonstration efforts that were conducted under Weapon Systems and Platforms program area. This program area has essentially 5 focused areas, which include surface engineering and structural materials, energetic materials and munitions, noise and emissions, waste reduction and treatment in DoD operations, and lead-free electronics. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. Remaining webinars for 2019, and there are only a couple of those, will cover CERDIP and ESTCP efforts on developing and demonstrating PFAS, for poly and perfluoroalkyl substance, treatment technologies, and monitoring and treatment of groundwater contaminated with chlorinated solvents. You can access a list of 2020 webinars shortly at the link shown here. I would like to remind everyone that a copy of the presentation of today's session can be downloaded from our webinar page. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. And I'm pleased to announce that the CERDIP and ESTCP Symposium will be held this year in December in Washington, D.C. at the Marriott Woodland Park. And this 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the CERDIP and ESTCP website. Enjoy today's webinar.
Thank you, Robin. It is now my pleasure to introduce today's first speaker, Ms. Liz Hasselbeck, who is a senior research scientist at the Naval Surface Warfare Center, Carderock Division in Maryland. Liz is a subject matter expert on the mitigation of biofouling on underwater systems, including vessel hulls and appendages. She has served as an engineering manager for the technical warrant holder for coatings at Naval Sea Systems Command, a biofouling team lead at the Naval Surface Warfare Center, Carderock Division, and also as the PI on numerous research grants focused on biofouling control. Liz has co-authored over 40 research papers and book chapters. She earned a bachelor's degree in biology and French from McDaniel College in Maryland, and a master's degree in marine science from the American University in Washington, D.C. Liz, please proceed.
Thank you for the kind introduction. Slide 16. Today, I'll lay out an agenda. I'm mostly going to introduce the concept of what biofouling is and how we currently manage it, and how biofouling is impacting Department of Defense vessels. I'll be introducing the concept of hull cleaning, which is something that is applied to the coatings that are used on the underwater hulls of DoD vessels to help the performance of the coating along when it doesn't work well on its own. In this combination of coatings and cleaning, we have some important data gaps which I want to explore. And those lead us to where we are today, which is this need to develop a screening tool, a standardized device and test methodology to close some of these important gaps. And I'll finish with some conclusions and look forward to taking some questions. Slide 17. What is biofouling and how do we manage it and why do we care about it? Biofouling is the attachment and growth of organisms on immersed and man-made objects. The Department of Defense uses biocide-containing anti-fouling paint systems to control biofouling on the underwater hulls of their vessels. The primary coating system that's in use is called a copper ablative underwater hull coating system, or anti-fouling paint. These paints are designed to release the biocide cuprous oxide at an effective rate or dose over time, and to prevent essentially the settlement and growth of these marine biofouling organisms. The coatings are fairly effective, although they're somewhat of a older technology, but they eventually, especially on DoD vessels that don't have a very high activity profile, they eventually are overcome by biofouling and some growth will occur. It only takes a little bit of growth of biology to create a roughness that has a negative impact and a measurable impact on ship performance, especially hydrodynamic drag, which is going to impact speed and fuel efficiency and these sorts of things. So we mitigate this fouling through the use of in-water cleaning. The in-water cleaning of ablative anti-fouling coatings serves multiple purposes. One, it removes the biofouling, which is the immediate problem. But fortunately, it also tends to reactivate the coating by removing what we call a leached layer through this abrasion between a rotating brush, for example, and the coating surface. So this restores the rate of release of the biocide and extends the effective service life of the coating. There are some environmental concerns about this process that I'll identify later. Slide 18. So biofouling not only has this negative effect on fuel efficiency, but it also can negatively impact speed, range, and maneuverability of vessels. And when we're in the process of mitigating biofouling that does accumulate during these maintenance events, the ship is essentially taken offline and it can't be used for its intended purpose. Although those cleanings don't take a long time, they do require the ship to be pierside. Biofouling also has negative effects on signatures and if we're using energy and fuel to overcome the roughness and drag associated with biofouling, we're not able to use that same energy for our military intent. There are air and water quality concerns that center on biofouling control that I'll highlight as we go through. Slide 19. The primary technologies, as I mentioned, to control biofouling on the underwater hulls of ships are coating systems, and there are several types which I'll address soon, combined with this cleaning or maintenance. So you see in this image the materials and maintenance aspects of what essentially amounts to a set of interdependent variables that come into play in the whole biofouling scenario. The efficacy of coatings is tied closely to ship activity and inactivity and where the ships are located. That would be the movement component of this image. The efficacy of maintenance is tied to the type of tool, the trigger for the cleaning, and the timing of the cleaning, which is also going to be tied to ship activity or movement. Monitoring is a key aspect of characterizing the performance of these technologies, understanding their service life and benefits, but it's quite challenging because they're so closely linked together. Slide 20. So there are the copper ablative anti-fouling paint technologies that are out there that contain these the biocide cuprous oxide, as I mentioned, but there are also new coatings that are on the market that contain other biocides, sometimes combined with cuprous oxide, but sometimes without heavy metal biocides. These organic pesticides are of high interest because of the reduction in the amount of heavy metal used, but also they have a shorter environmental half-life, which could be beneficial. There are also some biocide-free coatings on the marketplace. The primary technology is called fouling release. This is a low surface energy coating that minimizes the ability of biofouling organisms to well adhere and stay well adhered to the surface of the coating. These have been evaluated for DoD use but aren't in wide use. they're not a particularly good fit with our operational profile, as our ships spend consecutive weeks and months alongside or in a harbor at times, and so it's not a good match. There are some hybrid coatings being introduced to the U.S. market that have some fouling release aspects combined with some biocides. So entering the U.S. market today are a high number of advanced coating systems that are of high interest to the Department of Defense. There are basically three categories of regulatory concern that center on biofouling control. One is the leaching of the biocide into the water, and if that has if the biocides don't have the right properties, this can be a problem. There are also operational considerations with biofouling. I mentioned the fuel efficiency, which has an air quality component to it, that is the increase in combustion emissions tied to the poor fuel efficiency. And then there's the potential for operational ships that are biofouled to potentially transport species across the globe, which could become invasive species. The second main category of regulatory concerns centering on biofouling control is the drive to take the ships into dry dock. And there are some important waste streams associated with coating replacement in dry dock, and they're primarily tied to air quality in the context of volatile organic content or solvent, as well as hazardous air pollutants. And then there are water quality waste streams, the spent abrasive that's contaminated with the biocide, and any kind of water that might enter the dry dock, and that water leaching the biocide and ultimately ending up in the harbor or waste treatment plants. And then the third category of regulatory concerns centers on cleaning. The in-water cleaning is known to remove a small amount of paint, especially well known for the ablative coatings, and those inputs can end up in the harbor. They're also removing the biologics, and the ability of the biology to survive the cleaning process isn't particularly well known. Slide 21. So when a hull cleaning fails, when a hull coating system fails, we execute these cleanings. Now they could be executed in dry dock, but that would be very expensive and time consuming. And I would suggest that for DoD vessels, because that's what I'm most familiar with, there would not be enough dry dock space available to execute the cleanings with the frequency that they're needed. So in-water cleaning is the low-cost solution. It's relatively quick and relatively low cost, and the benefit of it is well documented. The payback period is quite short, especially in the context of fuel efficiency. Slide 22. The Department of Defense, and in particular the U.S. Navy, have a long history with in-water cleaning. We've been conducting cleanings on different paint technologies since at least the 70s. We don't want coating failure and biofouling persistence to be the driver that brings ships in for dry docking. So we've underpinned the performance of these coating systems with in-water cleaning, primarily with rotating brush tools, one of which is shown in the lower left picture on this slide. These coatings have enabled and underpinned the ability of our Department of Defense vessels to go longer periods of time between dry docking, which is a positive and a huge cost saver. Slide 23. The rotating brush tools that we currently use are something that can be applied whenever sufficient biofouling triggers a cleaning. Most U.S. Navy ships, at least, undergo inspections nominally twice a year. Not at every inspection, there's not necessarily a cleaning done of the underwater hull paint system. The cleanings are triggered by a combination of a fouling rating, which is an assessment of what type of biofouling is present, and a percent cover of that rating. So the trigger for an anti-fouling hull coating cleaning is a fouling rating of 40, which is small calcareous biofouling, over 20% of the hull. And for a fouling release coating, it's a fouling rating of 50, over 10% of the hull. As I suggested, we primarily use rotating brush tools for anti-fouling paints, but we've determined that water jet tools are the proper tool to use for fouling release coatings, but they're in limited use, so we don't have particularly mature water jet cleaning technology in our repertoire. Slide 24. The benefits of in-water cleaning I've already described, removing the biofouling as well as restoring coating efficacy. But there are these consequences: the discharge of paint components, the impact on coating integrity, especially paint thickness, and for fouling release coatings and brush tools in particular, a negative impact on surface properties. So slide 25. So we need to find the right solution. We need better metrics to understand the impact of cleaning tools on hull coatings and their environmental inputs, because environmental regulations represent a constraint that affects this 4M's interdependent variables image that I've already shown. Slide 26. So what is it that we don't well understand? Well, our lack of understanding in terms of in-water cleaning is primarily linked to how the cleaning tools affect coatings that we haven't been using for a long time. These coatings that I mentioned that are emerging into the U.S. market and are of high interest to the DoD. So we need to understand the impact on coating thickness change, any kind of damage to the coating, and potentially subsequent efficacy of the coating following a cleaning. But we also don't have a very good understanding of the actual environmental inputs from the coating cleaning, including both chemical and biological components. We also understand that this relationship is going to be affected by the combination of cleaning tool, coating type, and cleaning strategy. So we've identified a need for the standard test to quantify this relationship, because we've explored other tools and techniques that don't seem to be a good fit, which I'm going to describe. Slide 27. One option that we considered for understanding the impact of cleaning on coatings is this alcometer washability tester, which is commercially available, but primarily is used to evaluate the impact of standard cleaning brushes or other materials such as sponges on these architectural coatings. So it's not a particularly relevant tool for marine coatings that are used on ships. The advantage of the tools is that we have a high quality data and the data are reproducible, but they're of limited relevance for us, and it would be very difficult to measure the associated environmental inputs that are of high interest to us. Slide 28. Something that we have tried and we have a decent amount of experience with for the legacy copper ablative paints that we've been using for a few decades now is we can evaluate the thickness change before cleaning and after cleaning directly on a ship hull. The advantage here is that we're applying the full-scale tool to in-service coating, but the disadvantage to this technique is that it's very difficult to resolve small changes in paint thickness, and we have a very limited ability to assess the environmental input from the coating in terms of the particulate and the biocides. For the new coatings that are of high interest to us and that we're actively evaluating, it would be high risk to apply this technique to coatings where we don't have any familiarity with how they might respond to cleaning tools, because if the impact is quite high, then we have basically a bare spot on our hull, which would not be desirable. Slide 29. Another option for testing that we've used and tried is what we refer to as a raceway test. So in the upper right, you can see there's essentially a panel, or it's about the size of the wall of your average meeting room. And in that raceway, there's a removable panel to which we can attach some test paints that are on test panels. And then we can run the full-scale tool across those test panels, and we can remove them for up-close analysis. So the advantages of something like this are that we can apply the full-scale tool. The data are very high quality because we can control exactly how the paints are applied to the panels, and there's no risk to the ship. The disadvantage is that it's quite high cost. A lot of infrastructure is needed, and there are only a limited number of places where you can do this kind of testing. And then there's a limited ability to measure any kind of environmental inputs. Slide 30. This just provides a few more photos of the raceway test, and you can see on the image number 3 is 10-inch by 12-inch panels that have been bolted to the removable frame. Slide 31. So this brings us to where we are today, where we're, oh, I'm sorry, take that back. I forgot there's one other option for testing that we have evaluated, and that is a diver handheld tool. We'll go to slide 32, and then when I say, we'll come back to 31. This is a schematic of the handheld tool. The height of the sample chamber here, just for scale, is about 6 or 8 inches. So this is essentially creating a trapped volume of water. It's a tool that can be applied by the diver directly to the hull of a ship. We have a cleaning material at the base of the sample chamber, and then we have this crankshaft which allows us to rotate that cleaning head. You have a trapped volume of water with the double-edged gasket, so you can sample the amount of biocide or biology that is removed. Slide 31. The advantage to this type of tool is that you can quantify the biocide inputs, which is important. You could also quantify paint thickness change, but you're not getting the type of forces imparted on the paint that you would from a full-scale rotating brush tool. So you're not using the full-scale tools. Slide 33. So this brings us to the standardized device and method that is desired in order to fill these knowledge and capability gaps. We need to address the weaknesses of these other methods, and we want to be able to match the operational characteristics of the tools that are used in the field while also being able to sample the water quality for the biocides that are released. So as part of our ESTCP project, we detailed a large number of design requirements and we designed the tools to match the operational characteristics of the full-scale tools and be able to quantify the biocide released. Slide 34. This is a schematic of the tool that has been built. The tank is about 20 feet long and about 4 feet wide. So we have a trapped volume of water. The tank can be filled with seawater through the inlet valve and filled to the desired height. There is a trolley that can translate down the length of the tank, and essentially what it's doing is carrying a sample, which is the red rectangle in the trolley sample holder, and that trolley translates that sample across a rotating brush that is being powered by a brush drive in the sump. Next, slide 35. This is a close-up of the trolley and the sample holder. The sample, we made it so that the sample was something that could be easily replaced because we want to evaluate the impact of these cleaning tools on several coatings. And of course, we would like replication. Slide 36. The device is designed to pass the coated test panel over the rotating brush cleaning tool one time. And we've designed it so that we can evaluate multiple tool types, including a diver-driven multi-brush tool, as well as a diver handheld single brush tool. So we have different motors, different cleaning heads, and we will be evaluating 7 brushes in total in our initial testing and on 3 different coatings. We will be quantifying the changes in paint thickness or any other impact to surface properties, and we will be sampling the water quality for dissolved metals, particulate matter, and we're especially focusing on quantifying the amount of copper and zinc released. Right now, this is a screening test to compare the legacy products to emerging coating technologies, and there won't be any analysis of biological inputs, although that would be possible to do in the future. Slide 37. This is another view, a cross-section now of the tank, showing the motor that's going to rotate the brush in the sump, and then the trolley is shown overhead. The brush is not in place in this view. Slide 38. This is now a side cross-sectional view with the motor being represented by the orange rectangle and the brush being represented by the green triangle, essentially. And then you can see that we're basically showing here how the trolley translates the sample over the brush. Slide 39. So in conclusion, the underwater hull coatings that we use essentially require underpinning by in-water cleaning. And this is an effective and efficient combination of technologies until a better paint system can be demonstrated, validated, and transitioned. But there are some important concerns about cleaning, and there's a poor understanding of the impact of cleaning tools on coatings with which we don't have much familiarity. So we need an improved understanding in order to aid regulators and technology developers, as well as end users and stakeholders. So this standardized tool is and method is going to help inform the problem. The tool has potential uses beyond the current scope of the project, such as brush development, alternative cleaning tool evaluations, such as water jets. We could evaluate cleaning efficacy, that is the efficacy of biofouling removal. We could even evaluate biofouling survival or the impact on biological oxygen demand from the removal of large quantities of biofouling. Slide 40. The benefit to the Department of Defense is to establish a standardized method and protocol to close the critical knowledge and capability gaps, especially in the context of reducing the risk associated with new coating transition and helping our ability to predict coating system service life that is especially tied to the impact on paint thickness change over time. And then the assessment, and enable more comprehensive assessment of the use of in-water cleaning as a biofouling mitigation strategy. And it underpins the key environmental quality concerns that I identified, which are primarily rooted in air and water quality. slide 41. So I'd like to acknowledge my team at the Naval Surface Warfare Center, Carderock Division, our collaborators at the Naval Information Warfare Center in San Diego, California, as well as the contractor who designed and built the cleaning tool test device, which is Battelle in Columbus, Ohio. So with that, I can take any questions, and I thank you for your attention.
Thank you so much, Liz, for a great presentation. As a reminder, you may submit questions by using the Q&A box on your screen. We have received a number of questions that Liz is going to be answering, starting with a question from the Virginia Department of Environmental Quality at Tidewater Regional Office. Liz, in addition to copper as the primary and current biocide to dissuade the settlement of aquatic organisms on hulls of vessels, are PFAS, or per- and polyfluoroalkyl substances, also used on vessels' hulls as foul release coatings?
The chemistry of fouling release coatings is primarily silicone and fluoropolymer, but I don't think that the chemistry of the fluoropolymer is the substance that you asked about. But I could certainly answer a question like that in better detail in a side conversation, so I welcome you to reach out.
Great, thank you so much, Liz. This next question is from the American Association for the Advancement of Science. With the high number of new anti-biofouling agents of interest to DoD coming on the market, how does the DoD evaluate and prioritize their acquisition?
Right, so the biocides themselves go through a registration process through the Environmental Protection Agency. So the DoD first looks to the paint companies and the US EPA to find a acceptable level of risk associated with the combination of paint and biocide. So that's the first level of screening. Once biocides are registered with the US EPA, then the product that contains them is also registered, and there's a whole process for identifying the hazards associated with that. After that is complete, then the US Navy and other services work with the paint companies on essentially a continuous basis to look at emerging technologies, and we evaluate also sort of on a continuing basis whether or not these new advanced technologies might be able to outperform the legacy products. And each agency has its own budgets that allow them to screen and vet these products. On the Navy side, there's a performance specification for hull coating systems, and that lays out very detailed requirements for the makeup of the coatings, the use and application removal of coatings, as well as how the coatings must perform. So there are multiple levels of the process for inserting new technology into the fleets.
Great, thank you, Liz. The physical properties of antifouling coatings are different from fouling release coatings in terms of bulk softness and surface texture. Do you know which cleaning tool is best for fouling release coatings?
Yes, so we did an evaluation of that using that Raceway Test. We were not evaluating anti-fouling coatings there. We were evaluating fouling release. And we tested rotating brush tools as well as non-contact cleaning tools such as water jets. And it was found that water jets had the least negative impact on the surface properties of the coating, primarily scratches and gouges, for example, and that the follow-on performance of those coatings was favorable compared to the follow-on performance of coatings that were cleaned with rotating brush tools. Now, the Navy doesn't have any kind of qualified high productivity rate non-contact cleaning tool, say, based on water jet technology at this time. If we need a water jet cleaning tool, we literally use single nozzle water jets in the hands of divers. But our use of fouling release coatings is very limited, so we don't really have a high need to develop that type of technology.
Thank you, Liz. This is a question from the American Chemical Corporation. Can you modify the standard cleaning tool to get accurate copper and zinc measurements? And can you measure how much of the copper released is toxic versus the amount that is non-toxic due to complexation?
So for the latter question, I think that's complex and challenging, but I understand as a subject matter expert that that's an important aspect here. But all the regulations aren't necessarily written around available versus not available copper. In some cases, it's just, what's the total copper? But the first part of the question is, can we modify the existing cleaning tools to get the answers, to quantify how much biocide is released? And there is definitely, there's in the cleaning technology, tool development world, there's definitely technology being developed that captures the effluent from a cleaning, and from that you could probably get the answers to your question, but that's not the kind of technology that's primarily used in the DoD, so we haven't been able to answer that question yet. But I would imagine that in our future, we'll probably be answering that question.
Thank you, Liz. A question from the Resident Corporation. How thick on average are the coatings in question, and how often are they cleaned?
Okay, so the anti-fouling paint systems that are applied to the sort of larger Navy ships, that have a need to go, 8, 10, and possibly up to 12 years between dry docking. Those are 5-coat paint systems. The first 2 coats are epoxy anti-corrosive paint, and then the next 3 coats are the ablative anti-fouling. These requirements can be found in our performance specification, which is MIL-PERF, so that's MIL-PRF-24647E, and that's publicly available for you to look up. In terms of how often the ships are cleaned, our rule of thumb, although we don't have detailed enough metrics on this as we would like, is that the ablative anti-foulings generally require cleaning within the first 3 to possibly 5 years, and then more frequently after that through the service life. But so our rule of thumb is once in the first 3 to 5 years, and then several times, after that. But I don't have a firm number.
Great, thank you so much, Liz. We still have a lot of questions we haven't gotten to, and we'll get back to them during the final Q&A, but it is time to transition to our second speaker, Mr. John Escarsega. John is a research chemist and leads the camouflage coatings and corrosion team in the Materials and Manufacturing Science Division of the U.S. Army Research Lab in Aberdeen Proving Grounds, Maryland. John is responsible for initiating, planning, and performing coatings research and development for the Army. He has been involved in major formulation efforts that have dramatically improved durability and lessened environmental impact of camouflage coatings used within the DoD. His current work focuses on formulating coatings with near zero volatile emissions and enhanced multifunctional capabilities, including the elimination of heavy metals for pretreatments and primers. John has authored numerous open literature publications and has written and edited book chapters on organic coatings. He earned a bachelor's degree in chemistry from Mary Washington University in Fredericksburg, Virginia. John, please proceed.
Well, thank you, and good afternoon to everyone. I'll be the principal speaker today, but I also wanted to acknowledge my coworkers and collaborators, Mr. Fred Lapperman, ARL senior chemist in our group, and Mr. Daniel Pope, a materials engineer. Today we'll be highlighting our efforts in advanced coating systems for Army tactical assets. And go to the next slide, please. So today's agenda will be rather robust, but what we'd like to do is provide to you some background and then insight to how we implement technologies, and then literally walk you through our pretreatments, primers, and top coats. Even though we see them as a system, we'd like to talk about each one of them individually, and then touch upon some of our efforts in the data collection and modeling, and then wrap up the seminar. Next slide, 46. So very often we are asked, where are these coatings used, and how are they applied, and a number of other questions. But we wanted to give you a sense of the various areas. So not only do we apply these coatings on ground vehicles, but also the aviation, munitions, and a tremendous amount of support equipment to give you a gist of where these coatings are applied and used throughout the DoD. Slide 47, please. One of the key aspects that enables us to transition technology is not only our authority, but our leadership within this whole arena of CARC, or chemical agent resistant coatings. Essentially, we have an Army regulation, AR 750-1, that says that if anything is a piece of tactical equipment that would be going into the battlefield, it will have our CARC coating or CARC stack up. And along with that, we as the commodity manager are responsible for the various specifications and revising and creating new requirements that enables us to forward the technologies. Can I have the next slide, please, 47? So this picture, if you will, I think highlights some key areas, principles that we use. We often, such as CERTUP, may get drivers for the environmental arena, but we want to express that while we're doing that, we are in no way jeopardizing the survivability or the durability or making the application more complex. So all of these things go hand in hand to ultimately deliver a product to the field. Slide 49. To that point, we have two key specifications that we refer to as overarching specifications. The one on the left, 53072, is a rather large document, has a table of contents, and it's a go-to guide for applying these coating systems that we'll be speaking of. And is very detailed in regard to the type of substrate you would have, the cleaning you would do, and then the selection of coatings. The 490 spec is specifically addressing the pretreatments. So hand in hand, they capture all of our detailed specs with regard to our primers, our top coats, and all the coating systems that feed into these. It's a very, we find, a very excellent way to use as implementing or transitioning product. Slide 50, please. So what I'm going to do today is walk you through from the pretreatments we use that are supporting or passivating the substrate, and then talk about our primer systems, and then lastly our top coat. And the pictorial here is to highlight that while we see these as the traditional stack up, the future or the next generation of coatings is very multifunctional, and hopefully as we go through this you'll see exactly what we're speaking toward. Slide 51. So with regard to pretreatments, probably and most fundamentally the hardest or most difficult hurdle we've been addressing for some time is the elimination of hexavalent chrome. And what was capturing that was the spec 15328 that was often referred to as wash primer. And tremendous amount of solvent, tremendous amount of hexavalent chromium. And what we found was that as we explored alternatives, we found many alternative pretreatments that could be sprayed applied like the wash primer, and that provided equivalent or better corrosion resistivity. And through all of these projects that have been supported by CERDIP or from other agencies, once we get through the lab work or simultaneously lab work, we'll also be executing demonstrations so that we can see what these things are doing in the field. Slide 52. Another example that through this wash primer, we were applying it on support type of equipment and then exposing them outdoors, such as Cape Canaveral Air Force Station. Again, looking for severe environments and information as quickly as we can get it to discern whether these alternatives would be viable. Next slide. So often, and very often, especially for our steel substrates, we're looking at zinc phosphate, and again, for the spray application, looking for alternatives for that kind of more conventional pretreatment. Next slide, 54. I think this is very telling, where often we look for pretreatments, and then once we find that they work, probably, if it's not at the very beginning of the conversation, it certainly comes forth toward the end of the project as well. How much? How much is this going to cost us to make these changes? And if you direct your attention to the bottom line, we were doing a price, just itemizing every item, and you could see that in this particular case, for some of the pretreatments that we have approved and validated, it was virtually half the price. With similar performance. So perhaps the takeaway here is that that these greener systems or newer systems do not cost more than legacy, and I think that's often a situation of concern that people suggest or state that new systems cost more, and where we're finding that that's just simply a false statement. Slide 55. This is, I think, a very telling pictorial, if you will, of the existing type processes for both ferrous and non-ferrous and the multiple steps. And with our immersion, so I've talked briefly about the spray type pretreatment. Now I'm going to be shifting to immersion pretreatment. That we have zirconium type based pretreatments that are allowing us to have fewer steps and essentially can do both steel or ferrous and non-ferrous substrates. And for us, this was just a win-win across the board for the end users and the elimination of a lot of heavy metals. Slide 56, please. perhaps as you look at these slides, if I could guide your attention to the last few elements in both tables, essentially where we have heavy metal, it was nickel, we have for the zirconium pretreatment, there is none, no sealer, ambient temperature, minimal sludge. When you get at aluminum, similar hexavalent chrome, there is none, and in both situations, the temperature is at ambient, which provides a lot of benefit for cost savings to the facilities that are doing these kind of pretreatments. Slide 57. So I've talked about the spray pretreatment. Now we'll move to our liquid primers. As many of you are aware, we have a number of specifications that capture our liquid primers, specifically MIL DTL 53022. And in that spec, we have two types, the type 2 and 3. And over the years, these systems have evolved. So at one time, it was 336 hours in a salt fog, neutral salt fog, X number of cycles. And the premise had been, well, if we have more hours, more cycles, it's supposedly a better product. And that holds true to some degree. And yet, when we were going outdoors, we were finding sometimes that did not hold true. And so there's been a tremendous driver for us to do a few things. And one of them is to enhance the overall corrosion resistivity. And we're happy to announce that we are going to eliminate products types 2s and 3s and then only support type 4s, which have a longer number of hours in the conventional lab testing and number of cycles, but also outperforms an outdoor exposure. And so it's a major initiative for us, and we're really happy that that's going to be probably the strongest underpinning with regard to our CARC stack up. Slide 58. So with our liquid primers, we have a number of specifications, and then another system that we are supporting is E-coat or electrocoat primers. And in this case, as I had just described, for liquid, the hybrid, if you will, is type 4, and we're showing here that with the E-coat or 53084 specification, it's actually an enhancement or even better than the liquid. And it's expected. These things are typically an immersion type technology, thermally cured, has excellent edge retention, and just is a very stellar type coating system. And I would probably be accurate to say that virtually every car that is on the road has E-coat as one of the principal coating systems. It's a phenomenal type coating system. And again, we're looking now to take larger systems and scale it down so it's smaller tanks for immersion for small parts. 59, please. And to my point, here is just a schematic of the whole process. So we'll be able to take pretreatments that are applied and then use the E-coat as a primer system, and then subsequently bake it, and then have our top coat applied. Slide 60. So we've talked about E-coat, our liquid, and the other primary primer system is our powder coat. And again, these programs were supported by CERTUP, and we have both powder top coat and primers available. And again, in regard to durability, chemical agent resistivity, and supporting our requirements, this is probably one of the most robust systems. And so we feel that as things evolve, these are the types of coating systems we'll see more and more. Right now, it's a small percentage of our overall primers that are being used. Next slide, please. So, while we've been discussing our pre-treatments and our primers, what I'd like to shift into now is discussions of our top coats, and recognize that while we did that differentiation, it is and always will be a system. Sometimes I jokingly have mentioned that the top coat goes for the ride, and there is some truth to that, but the reality is that the top coat is truly the first line of defense from the exterior elements, and then obviously the pre-treatments and primers are doing their job to passivate the substrate or providing good adhesion. So when we begin a project, we often look at particular raw materials within the coating system. And with few exceptions, these are the 5 raw materials that are typically incorporated in coatings. The exception would be, for instance, powder, which would be solventless. But each one of these are a key aspect to the overall longevity and the meeting requirements, if you will, for top coats. We go to the next slide, 62. And very specifically, and I'll just pull out examples, there's a lot of effort right now to look at alternative resin systems that do not contain isocyanate. Even though it's a minute amount, there is some free monomer in the component B, typically in 2-component systems and block systems. And again, this is something that CERDIP and the various services have a lot of interest to look at alternative resin technology. The other area that I'll highlight is low solar absorbing pigmentation. We're going to be seeing much more of these types of pigments in the industry, just for autonomous type vehicles, for their sensors and detectors. And our interest is twofold. One, they act literally as a sunscreen where they inhibit photons from damaging the polymer system. And then secondly, by that very action, extends the life of the coating and supports our other requirements. I'll speak to this a little bit more, but the takeaway here is that our goal is that we will most likely be shifting the palette of our colors that currently exist to using low solar type pigmentation. The rest of these elements are areas that we're exploring and are using to enhance our overall coating system. Slide 63, please. So I appreciated the opportunity to discuss our stack-up, pre-treatment, primer, top coat, and I think I would not be exaggerating to suggest to everyone here that probably one of the most challenging situations that everyone is facing is the management and the handling of data. And so whether it's our emails, whether it's reports being sent, the data that we're collecting within our lab, at our outdoor facilities, it's just growing in leaps and bounds. And so there is a tremendous effort here within ARL and with the other services to begin using, just being more smart about that and incorporating artificial intelligence and creating models that will enable us to rapidly collect data and then assemble that data and then have that data available so that we can use it to make determinations of best systems and recognize where gaps may or do exist. And so hence these few bullets, as our folks are going out to our weathering sites, they're taking tablets, taking measurements, having field already embedded in the software, to assist in the corrosion ratings, and various requirements we're looking for, as well as taking color and gloss readings, bar scans, tagging, and all of this is feeding back into a larger database, and that is actively going on now. Slide 64. Again, just a picture, if you will, of a snapshot of what and how we're introducing that information. For us, we find this to be probably the most significant aspect, because it's going to be an accessible database for all of us, and I think an ability to look at the data in a much more deeper way than we ever have been able to do. Slide 65. In complement to that, CERDIP is currently funding programs, and we're participating in that. And if you look to the right there, we have 3 areas where we're putting data into. One is just in our fleet data, where we're having folks go into the field and making assessments on actual vehicles. The top sphere is coding data that we have had and we are collecting. And the last is just input from us with regard to the various substrates and the various types of coatings. But ultimately, this is not to do a chemical type modeling of degradation, but a prediction type modeling for our facilities and maintenance areas, so that we can quickly discern that if these pieces of equipment are being deployed in an area that's more corrosive or more harsh, we would already have an insight to those types of aspects and discern what may be the best coating stack up. Next slide. So, in conclusion, I think there's a number of points to be made, but I think these permeate to be the basis for what we'd like to share. That with the ownership of our specifications, that has enabled ARL to transition these various products and these various chemistries more effectively. We said this earlier, but I think it's necessary to repeat that while we're moving to a more environmentally compliant type coating systems, we're not reducing the performance. And we feel and find that these advances in data collection will assist in the interpretation with regard to what, quote, is happening, and will feed into the development and implementation of new coating systems. Next slide, please. And I would be remiss to suggest that the work we do just remains onto itself. I feel that very often we're very guided by a number of drivers, and I think we're very proud to express that as we advance these coating systems as stewards to the environment and to end users, and most importantly, support to our service members, men and women in our service, that when we capture environmental compliance and enhance these coatings without negative impact, that is just a tremendous win-win for everyone. And finally, I'd like to express our tremendous appreciation for industry, academia, and our other services that continuously collaborate with us. And as a group, we cultivate, I think, some of the best work with regard to supporting our warfighters. And so with that, I thank you, and would be happy to take any questions. Thank you.
Great. Thank you so much, John. We've received a lot of questions for you, starting off with a question from the Army Public Health Center, the Army Combat and the Army Combat Readiness Center. Are costs from durability, longevity calculated into your examples of cost effectiveness for greener products?
Typically, yes, and it is rather a loaded question in that it takes time for us to put these coatings outdoors and then do that comparison where if something lasts, let's say, 3 years and a newer product would last 3.25 years, there would be a delta. So typically, many of our programs have these return on investment templates that we can use. And so at the very beginning, we input those values, and as we get more data, we input that kind of information.
Thank you, John. Here's a question from Boeing. Can the same cleaner and deoxidizer be used on both steel and aluminum before the application of the zirconium coating? And what cleaner and deoxidizer are you using?
Typically, yes, and I probably would like to address those offline as far as some of those specifics, because I think we'll quickly get into the chemistries of things.
Great. So John's contact information can be found on the slide prior to this. So if we could pull that up, I would ask that the gentleman from the Boeing Research and Technology reach directly to John for a response to this question. Here's a question from the American Energy Technology Company. Has zinc powder been eliminated from the liquid epoxy bisphenol primer?
Could you repeat that? Has the zinc powder been eliminated from?
The liquid epoxy and bisphenol primer.
So I'm not clear what they're meaning by zinc powder. So we do have zinc-rich type coatings, and I'm assuming they're referring to our liquid coatings. Some of the inhibitors have zinc compounds, but they're nothing to be concerned of leaching, etc. They're just many of the go-to type corrosion inhibitors. Again, if they'd like to contact us, we could talk more about those details.
Sounds good. Thank you so much, John. Okay, so the next question is from Eastern Michigan University. Does DoD have publicly available data on life cycle assessment, such as life cycle inventories?
We do, and that probably the most pertinent data would be through our Ground Vehicle Systems Center folks. And with regard to publicly available, I don't know to that extent, but I know Eastern Michigan, we work with them, so they would probably have some availability to those kind of details.
Great, thank you. Another question from Boeing. How did you check corrosion resistance of the pre-treatment?
Basically, typical standard neutral salt fog, the GM 14872 cyclate corrosion, and then those were obviously with the pre-treatment primer stack-ups, and then the outdoor work was the actual stack-ups with different top coats.
Great, thank you.
And I'll add to that that some of that initial work with those pretreatments were interrogating just the pretreatment itself as it was being applied. So there was a lot of analytical interrogation to that pretreatment itself, and then there was follow-on lab testing.
Okay, this is great. Given the interest, just judging by the questions that are coming and what you've presented, how can private companies engage with the Army Research Lab to submit samples for qualification?
Yes, thank you. There's a number of approaches, and so I'm going to just speak, if you will, somewhat off the cuff here. So whether you're a smaller company or a growing larger company, if you have a technology that you think would be of interest and is somewhat coatings related, the easiest and straightforward thing is to send us an email and express to us what you have and where you may consider it to be viable. Then what we'll do is look at the existing specifications we have and see if there's a slot, if you will. Let's just say somebody says, hey, I've got a top coat that has 0 VOCs, can be conventionally applied, and we think it's really hardened for chemical agent resistivity and can be pigmented any which way. So that would fall right into our conventional specification for one of our top coats. And then we would just simply do some screening to see if those claims are true, and then move forward with that. So that's typically if people are wanting to submit samples for qualification. And in parallel to that, there may be technologies that are truly novel and maybe breakthrough with regard to how we're doing it, and reset the paradigm, if you will. And so those we would be as interested, and we typically have that upfront discussion about, well, what could it do and how could we implement it and incorporate it into our existing systems. So perhaps in summary, we're very open and intrigued to see new technologies, and we handle them on a one-on-one basis, and look forward to people's interest.
Great, thank you so much. This is a question from the Resident Corporation. Are powder top coats currently used in the field in operations? And how do you touch up coatings if damaged?
Yes, they are. Currently, we have a few major vendor suppliers that are using powder. The wonderful thing about powder, even though it may be the initial base coat, that the touch-up can be with a solvent base. We have spray cans, or I think in the field they're referred to as rattle cans, and even small touch-up kits. So one of the challenges, and what we've always assured, is that there's compatibility with our top coat. So if you have a powder, you could go over it with a solvent-based system. As mentioned, powder is making its way into our inventory, and I think as more portable units are established, that will probably be the predominant type of coating system used on small parts. So thank you.
All right, and one last question for you before we pull Liz back into the discussion. Similar to what we asked Liz in terms of the Navy, how does the Army evaluate and prioritize acquisitions of new coatings? Is it a similar process to the Navy, or is there a DoD-wide process that you all follow?
There is a process, and perhaps sometimes it's not as defined, though where it begins is a coordination between our Ground Vehicle Systems Center in Warren, Michigan, and with the Army Research Lab as the CART commodity manager. And so if there's a tenet that we adhere to day in and day out is ensuring the readiness or availability of these coding systems. And so as we get feedback from our Ground Vehicle Systems Center folks and from people just calling in, and we recognize gaps or we're being tuned into particular threats that need to be addressed, then we develop the technology, or we evolve the technology, or in some more simpler cases, just simply revise the specification to meet the new requirement. And the latter is typically like with environmental drivers, where VOCs or volatile organic compound content is being requested to be lower, and we just start looking at alternative solvents. In more demanding situations, like trying to harden systems to be more chemical agent resistant, there's a much more activity, and then it brings in other centers like the Chemical Biological Center, ARL, and then Ground Vehicle Systems Center. So it's a combination of that there's a set template, and yet when there's a need, then the various entities that can contribute then work together. Thank you.
Thank you, John. At this point, we'd like to pull Liz back into the discussion. And Liz, let's just get started with a request for you to please summarize the next steps in your work for the ESTCP project. And if you can also describe the timeline for those steps, that would be really great. Liz?
Yes, thank you. We literally just delivered the tool to the site where the testing will occur, and we are currently getting familiar with it. But in the coming 2 quarters, we plan to start evaluating the response of our coatings, which we're evaluating 3 coatings. And we will be doing repeated measures on those same 3 coatings over the next approximately year. And then part of our testing is also to validate what we find with what we're calling the cleaning tool test device by doing some full-scale assessments on ships to try to get as much of an apples-to-apples comparison as we can across the types of data that we're collecting.
Great, thank you so much, Liz. And a question for both you and John that we'd like you to answer, and we'll start with you, Liz. What is, in your opinion, DoD's greatest recent success with respect to coating developments? Liz?
So for underwater hull coatings in particular, which is my area of expertise, the Navy in particular, and also the other DoD groups have benefited most from what we call copper-free ablative anti-fouling technology. These are biocide-based coatings that don't have any cuprous oxide in them, and what they've allowed is effective biofouling control on aluminum-hulled vessels, which, if aluminum-hulled vessels would be coated with a cuprous oxide-based paint, there would be what we believe an unacceptable risk of galvanic corrosion. The only technology that was available up until the time where we transitioned copper-free ablatives were the fouling release coatings that I mentioned in my talk. And these were not a really good fit for these aluminum-hulled vessels. We know we have some data from both Navy and Military Sealift Command that indicate that the fouling release was not a good fit. So copper-free ablative was a really nice transition.
Wonderful, thank you, Liz. And John, would you like to weigh in, please?
Sure. I think there's actually two key areas, and the first has been alternatives to hexavalent chromium as we highlighted, both with our spray applied and then our immersion that's providing pre-treatments for both aluminum and ferrous substrates. I think that is just significant because we can confidently state that the Army no longer supports hexavalent chromium and that our current stack up can be, from pre-treatment upward, can be hex chrome free. The next area that's in complement to that, and is you'll be seeing more of this in the next 2 to 3 years, but plans are underway to change the color palette for the Army and using the LSA type pigmentation as our palette type pigments. So I think in complement, what you will see is an extremely robust coating that can be tuned for our particular requirements as those requirements change. Thank you.
Well, thank you so much to both of you for a fantastic webinar. As Robin mentioned, our next webinar is on Thursday, November 7th. That's next Thursday. It is going to be in the Environmental Restoration Program area, and it will detail results from DoD research efforts on developing innovative approaches for the treatment of waste derived from PFAS subsurface investigations. The webinar will feature 2 speakers. Dr. Andrea Leeson from CERDP and ESTCP will provide a status update on PFAS efforts with a focus on highlights from projects funded by CERDP on managing investigation-derived waste. Dr. Leeson will also provide an overview of upcoming CERDP and ESTCP PFAS-related solicitations and will discuss important CERDP and ESTCP publicly available resources on PFAS. The second speaker on November 7 will be Dr. Dave Major from Savron, and Dave will talk about PFAS destruction through smoldering combustion, which is a sustainable and cost-effective technology to treat PFAS contamination in soils and in investigation-derived waste. Registration is open, so please visit the CERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would really appreciate it at this time if you can take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your time.